Hello, and welcome to today's topic, which is van der Waals equation of state. So, I have done and already written it in my OneNote notebook here, and I have also copy and pasted a PV diagram with some isotherms, just the general one here, all right? And, well, the reason why I wanted to talk about van der Waals equation of state is because uh, it's my homework, and also because you can do some cool stuff with it. There's some cool things that van der Waals found out through this equation, right? So let's say, hypothetically, I wanted to use this formula, right? Well, I could supply it the temperature and the specific volume, right? And R is constant. Well, I can put that in, and well, we run into an issue. Uh, what would I put in for B and A? Who knows, right? I don't know. And at this point, well, I could look it up for that compound, right? But that we're gonna try to be van der Waals here, all right? And we're gonna solve it mathematically. Probably not the way he did it, but we'll do it our own way. So what do we do? And well, that involves the PV diagram here. So there is a specific isotherm on this PV diagram that will help us sort of find a path for us to follow to that will eventually lead us to the values for A and B. And it might be a little hard to identify which one that is, especially if you're running into this blind, right? You're trying to win a Nobel Prize, and well, that's pretty hard. So just uh, just to say it up front, it is going to be the isotherm, the critical temperature isotherm, right? The one that holds the critical point. And the reason it's so special is because, well, uh, there's a lot of information that you can get from it just by looking at it, right? So it's this one right here with the critical point, right? And then there's two key pieces of evidence or information that will help us lead the way to the values of A and B. And the first one is that, well, if you're looking at the critical point here, you'll notice that it gets flat here. And, well, what does it mean when a function of some sort goes flat at a certain point? Well, the first derivative must be 0, right? And for now, our reasoning is going to be simply just that it looks like it went flat there. So the actual reasoning for the first derivative being 0 there is a little bit complicated. And as far as I was told, that will be my reason. So there's that. The first derivative at that critical point is 0. And another thing you'll notice is that this left region of the critical point is concave up, right? But all of a suddenly, to the right of the critical point, it goes concave down, right? And well, what does that mean? Well, uh, concave up to switch to concave down is an inflection point, right? And well, an inflection point is really important for second derivatives. Reason being, an inflection point on a function represents that the second derivative at that point is 0. And so all of a suddenly, now that we've identified these things, the critical point is has been really important for leading us on a path that will help us find A and B. Because of us looking at the specific function for the isotherm at the critical temperature, we have identified two potential functions, the first derivative and second derivative of the equation of state at the critical point, has given us some equations for our two unknowns, A and B, two equations and two unknowns. And uh, we'll sort of work through that and see what this sun path leads us to. And I'll do that with you guys on the whiteboard. So let's get to it.
All right, so Welcome back here, and I've written our equation of state from van der Waals here, and like I said, the first derivative and the second derivative both equal 0. So, well, what are we going to do with that if we don't have the first and second derivative? So that's going to be our first step on our path. All right, and let's find out what the first and second derivative are. And well, for an isotherm, the temperature is going to be constant, right? And well, the two things that are changing are going to be the pressure and the specific volume. One other thing that we have to notice and realize here, and we have to make sure we point this out, right, is that, well, it's only those derivatives are only 0 at that critical point, and maybe somewhere else, but we only know for sure at that critical point. So because it's only at that critical point that the derivative is 0, we have to realize that the values that we're going to be working with are the critical properties, because it's only 0 at the critical point, right? So let's begin. So we'll be taking partial derivatives, right? So the partial derivative of the critical pressure, right, with respect to the critical specific volume is going to be, well, these are constant, right? So I'm going to do this a little slow. I'm going to try to write out all my work so you guys can see kind of where I went with the steps, all right? So R and critical temperature are constants, right? So you can pull this out. So right now we have V minus B -1, right? So we do some U substitution, right? V minus B equals U. Du equals dV, right? So then U to the negative is simply negative U to the 2, -2, right? And our U was V minus B. So we can put that in as V minus B squared and negative. I'll move this so it's a little bit more centered. Negative R TC. And A is a constant, right? So we can kind of take that out. And now we have V to the -2. Derive that. That's pretty easy, right? Times -2, V cubed, right? So now we have times 2, -2, V cubed. That kind of looks good. Right. Now we have first derivative. And like I said, this is equal to 0. And remember, only at the critical point. Now let's get started on our second derivative, right? So, partial, some notation here. All right. So negative RTC is a constant, so we don't have to worry about that. U substitution again, it's going to be U to the -2, right? Bring that down, -1, so -2 U to the -3. So it's going to be -2 times negative RTC. So we have 2 RTC and U to the -3. So VC minus B cubed. All right. 2 A's are constant, so we don't have to worry about it when we're deriving. So it's going to be VC to the -3. Bring it down. -3. At -1, VC to the 4. So we're going to get VC to the 4. And that's going to be -3 times 2A. So we get 6A, and that's going to be plus. And now we have our first and second derivative, and this is going to be equal to 0. Remember, both only being 0 at the critical point. Now, what can we do? All right, well, we can actually make these into some useful equations, right? So let's do that. Both can be transformed in the same way, both 0 on the opposite side there. So almost forgot that. That's supposed to be plus because -2, right? Almost. Sorry, error. Fixed it. Moving on though. Good thing I noticed. Let's do some. And that also fixes this. All good now. So we can do some rearranging and get some equations, some equalities, right? So we can move this over and we can move this over, and then I'm gonna write it in the form so that they're similar to each other, right? So they're both positive anyway. So all right, I want to cover the whiteboard for a bit here. I'm not doing anything sketchy. All right, some simple rearranging. And now we have our two equations for our two unknowns. And this time we won't need Python. It'll be pretty easy this time around. And I'm going to need some space for that. So I will be erasing this entire left side. All right, so we have our two equations. What can we do with that exactly? Well, if you notice, we can multiply this equation to that equation, right? We can multiply this with that, and we can multiply this with that. And the only reason we can do that is because, well, these two things are equal. We're doing the same equal things to each other, right? And hopefully you saw that. Hopefully the lighting isn't too bad. Anyway, so we can do that, but obviously that won't do much because, well, we're just putting the same things, right? So one cool thing that we can do is actually make this the inverse. So let's do that. I want to cover it up real quick. I want to cover the whiteboard while I write this. And, well, if we do that, if we do multiply now, we'll get a bunch of cancellations. So let's do that. We'll be multiplying this with that. Multiply. That looks like a plus, but okay. All right, so let's do it, right? So we will get I will write out all of it without doing any cancellations, just so that we see what is going on. All right, and this is, oops, almost forgot. All right, and this is what we get. All right, if everything was weird, well, it's because my recording crashed for the second time, and well, I sort of resumed where we were last time, and well, we were canceling stuff because we had just multiplied our two equations, one the inverse of that original equation, right? And now we're gonna find some cancellations. So What cancels here? Well, this quantity cancels with only one left on top, right? BC minus B. I don't need the parentheses there, but whatever. And just the 2 is down at the bottom. Our A's cancel, all but 1 on the top VCs, and this turns into 1/3. So BC over 3. And now just simple algebra at this point, right? So 3C, 3B, 2BC. I'm gonna go a little fast. And we get B equals VC over 3. And bada bing, bada boom, we have our first unknown. And with our first unknown, well, we can plug it right back in and find our last unknown, which is A. So let's do that. Cover the whiteboard just for a moment here. All right, so let's get to solving it, right? I'm gonna move the v cubed over and solve the fraction mess at the same time here. So I will do that. And well, VC, that's 3, basic 3 VC over 3 minus 1 singular VC over 3. You get 2 VC over 3. Square that, so you get 4/9 VC squared. That is all equal to 2A. Well, we don't want the fraction in the denominator, right? So you do some inverse work. So you get 9/4. Some of our VCs cancel, leaving 1 VC at the top. RTC VC equals 2A. And divide 2 over. And we get bada bing, bada boom, our last constant. And well, we've done it. We've solved for A and B. And with that, well, the crazy thing. With that, we can now find, we can now predict any pressure at, well, we now predict the pressure at any temperature and volume now that we have A and B, right? We can just plug in wherever we want, and well, there we go. Equation of state. Works, right? And well, that isn't really all of it yet. Van der Waals did something pretty crazy. So Van der Waals decided to take it even further beyond with his work, and was like, this equation can do something super. So what is that, you might ask? Well, we've been solving for the properties, right? The critical point properties, the critical temperature, critical pressure, critical specific volume, right? Well, there's this property, not specific to an ideal gas, but we'll introduce it of the ideal gas, and that's the compressibility factor, right? Labeled Z. And that's PV, I need to write it that, PV over RT. And for ideal gases, it should always equal 1, and that's for ideal gases. Well, he was like, man, let's find the critical compressibility factor. And you're, well, how do you do that? Well, let's plug our A and B back into our equation of state for the critical point, right? Because we're finding the critical compressibility, and see what happens. So I'm going to erase all of this, and we'll get to that. All right, so welcome back. Let's do that critical compressibility fancy work now, the further beyond. So we have our, remember, this is at the critical point, it only, right? So over V minus B, right? Minus A over V C squared. There's our EOS for our Van der Waals. And well, like I said, let's plug in our B and A's, right? So this might get a little messy. So BC minus BC over 3 minus 9/8. Well, let me put that on the outside here. 9/8 RTC BC over BC squared. All right. Let's simplify some things, right? First things first, the fraction. We don't want that down there. So we get 2/3 BC minus 9/8 RTC. And that cancels BC. Let's get that fraction out of there. So you get 3/2 RTC BC minus 9/8 RTC BC. And, well, look at what we have here. We just have two fractions subtracting from each other, right? So let's find their common denominator, 8, right? It's going to be PC equals 8 times 4, 12, minus 9 is 3 RTC VC. Now, how do we get the compressibility factor? Like I said, the formula earlier was Z equals PV over RT. And, well, since we're dealing with the critical properties at this point, well, it's going to be PC, critical pressure, times critical specific volume, over R times the critical temperature, right? And, well, that works out, because we can just move it all over, right? We can move all of this over here. And that leads to equals the critical compressive factor, and voila. I hope the glare isn't too hard. It might be. I'll write over here. And we found a singular number, 3/8. Well, what does that mean? Well, van der Waal, taking it further beyond, basically said that, well, the compressibility, critical compressibility factor for all compounds, because remember, we did it in a general way here, we've been solving in a general way, is 3/8 for every and any compound. And that's pretty nuts, because now we basically can determine a bunch of stuff without even really knowing some of it, because now we know that this is 3/8 for all compounds, right? And that could help scientists figure some stuff out that might have holes to begin with. And, well, yeah, so that's pretty crazy and pretty Nobel worthy, huh?